Here are our solutions to homework set number 6 for ECE 341. This homework deals with Laplace transforms and continuous probability density functions. Now the first problem deals with something you run into in circuits and signals and systems. Given a transfer function from x to y, that represents a differential equation. What is that differential equation? Well, s means derivative, so if I take the denominator cross multiply it all out, then sy represents derivative. So this is the second derivative of y, the first derivative and just y, the derivative of x and x. So that transfer function is the same thing as this differential equation. I could also write it in this form. Part B, if the input is a sine wave, find the output. This isn't really a Laplace problem, this is a phasor problem. With phasors, this is the gain everywhere. All I care about is what's the gain at a very specific frequency. The frequency is 4 radians per second, so s equals j4. The input is 2 minus j3. In phasors, the real part is cosine, minus j is sine. Multiply the two together, I get a complex number. What that complex number means is the real part is cosine, minus j is sine. So there's the solution. Part C says, find the output if the input is a unit step. That actually is a Laplace problem. So here's the transfer function, the gain from x to y. Take the Laplace transform of u, I get 1 over s. And the difference here is x is 0 for time less than 0. That means Laplace. Whereas in part B, this is true for all time. So I have this. That's not my table of Laplace transforms. So use partial fraction expansion. To get the s term, I cover up the s, plug in s equals 0, get 2/3. To get the s plus 3 term, I cover up the s plus 3, plug in s equals minus 3, I get 0.4762. And to get the last term, cover up the s plus 10, plug in s equals minus 10, evaluate, I get minus 1.14. Now this is my table of Laplace transforms. Taking the inverse Laplace transform, that's 0.667 times 1, 0.476 times e to the minus 3t, minus 1.14 e to the minus 10t. Problem 2 says, suppose let x and y be related by the following transfer function. In this case, I have complex poles. What's the differential equation relating x and y? Again, multiply it all out. S means derivative, so this is second derivative of y, 6 times first derivative, 109 times y, and basically no different. If my input is a sine wave, again that's phasors, this is the gain everywhere. Analyze it at the frequency of the input, analyze it s equals j4 times the input, times 2 minus j3, multiply it all out, I get a complex number. The real part is cosine, minus j is sine. So for phasors, real poles, complex poles, doesn't really make a difference. For part C, if I have a step input, that's where I do use Laplace transforms. Now do a partial fraction expansion. To get the constant term, plug in s equals 0, cover up the s, evaluate, I get 1.83. To get the s plus 3 plus j10, cover up this term, plug in s equals minus 3 minus j10, I get a complex number. In this case, polar form actually works better. And its complex conjugate over here, taking the inverse Laplace transform, that's just 1.83. This one is twice the amplitude, 2 times 0.95. The real part is your exponential, complex part is the frequency, and for the phase, it's the phase over the minus j term, plus 163 degrees. Problem 3 says, suppose I have this PDF, scale it so that it's a valid probability density function. What that means is the area has to be 1. If I take it as is, the current area is 2.2, so this area is 0.8 times 1, 0.4 times 1, and a triangle, the area is 1/2 base times height. Add it all up, I get 2.2. So to scale it, all this has to be times 1 over 2.2, or times 0.4545. So this really ought to be 0.4545 and proportional. Then it's a valid PDF. Problem 4. Determine the corresponding CDF. So the PDF, I'm going to express these as functions. This is 0, that's 0.8, this is 0.4. This straight line, the slope is, well, going back to 1. I'm going to scale it when I'm done. Just makes it easier this way. So here the slope is by 1 in 1 second, so that is equal to x. Plug in x equals 3, I should get 0. So x minus 3 is this guy. And in this curve, the slope is minus 1, so that's minus x. Plug in x equals 5, I get 0, plus 5. So this is your piecewise linear function. And that's 2.2 times the PDF divided by 2.2, and you get the proper equations. Now to integrate, the integral of 0 is 0. Integrals of 0.8 is 0.8x plus a constant. Pick the constant so that at the point where they join at 1 is continuous. This is equal to 0 at 1. This also has to be 0 at 1. So it's 0.x minus 0.8. Integrate 0.4, I get 0.4x. When x equals 2, it needs to be continuous. When x equals 2, this is 0.8. This is plus a constant. Plug in 2, I should get 0.8, so the constant is 0. Integral of x minus 3 is 0.5x squared minus 3x plus a constant. If I evaluate at 3, I should get 0.4 times 3, 1.2. Times a scalar, 1.2. Plug in x equals 3. This also has to be 1.2. There's your constant. Integral of 5 minus x is minus 0.5x squared plus 5x plus a constant. Plug in x equals 4. I get a number for x that has to match in this region. And finally, the integral of 0 is 0 plus a constant. This goes up to 2.2 at the end. When divided by 2.2 goes to 1. This has to match. So it's 2.2 divided by 2.2. It's 1 for x greater than 5. Checking in MATLAB, I create a function called CDF. I'll have a bunch of if statements. I'll pass x and return the CDF, the integral. So if x is less than 1, I get 0. If it's bigger than 1, less than 2, here's the equation. If that fails, bigger than 2, less than 3, bigger than 3, less than 4, bigger than 4, less than 5, bigger than 5, then scale it at the end, so it's a valid PDF. And to check it, I can say let's have x go from 0 to 6, steps of 0.01. Find the CDF at each value of x, and then plot x versus the CDF. And this is what it looks like. So it starts at 0, goes to 1, follows that slope. Looks pretty good. So what this does is, given x, I know the CDF, which is x. If I want, I'm going to, given the probability, find x. Here I'm going to use interval halving. What that does is, given x, I can find the probability. If I have some probability, like right here, 0.7, find this value. I'm going to use interval halving. I'm going to take my first guess as 0. The second guess is 6. This guess is low. This guess is high. Now take the midpoint. Evaluate it. It's also low, so I replace the left endpoint with this one and repeat. Here's my left endpoint. There's the right endpoint. Take the midpoint. In this case, it's high. Replace the right endpoint. Take these two, take the midpoint, and keep iterating. That's what this does. My left endpoint is 1. The right endpoint is 5. Take the midpoint, evaluate it, and replace the left endpoint, if I was negative, right endpoint it was positive, and repeat 20 times. That's one way to do it using interval halving. I can now generate 20 random numbers. So pick 20 random numbers for the probability, and then for each number, do the opposite. Given the probability, find x. Then when I'm done, plot x and p with an x and display it. So here's the probabilities, numbers between 0 and 1. Here's corresponding x. And if you notice, back on the PDF, most of the time I'll have numbers between 1 and 2, or close to 4. That's where I have the highest probability. If I look at this, quite a few of the numbers are between 1 and 2, and close to 4. So that checks out. Problem 6 is find the Laplace transform of p of x, also known as the moment generating function. To do that, what I'll do is I'll differentiate. And if you recall, the original function looked like this. It was a stair step, went back down, then a triangle. Take the derivative, I get a delta function. Negative delta, negative delta. The slope in this case becomes 1. Again, it's times 2.2. The slope going down is minus 1. That gives you the red line. The delta functions I like. I know what the Laplace transform is. It's just 1 times the delay, 1 times e to the minus s. This is equal to, well, times a constant, times 0.8. This is 1 times e to the minus 2s, 1 times e to the minus 3s, times the amplitude. The rest of it I don't know yet, so let's take another derivative. This one goes up by 1, goes down by 2, up by 1. So with this, this is 1 at 3 seconds. This is minus 2 at 4 seconds, delayed by 4. 1 at 5 seconds, delayed by 5. Divided by 2.2 to make it a valid PDF. Integrate twice, because I had to differentiate twice to get here. To undo the differentiation, integrate 2 times. Back on this function, I've got my 3 guys right here. That's your 0.8 delayed by 1, minus 0.4 delayed by 2, minus 0.4 delayed by 3, divide by 2.2, integrate. So this is the Laplace transform of my PDF, also known as the moment generating function. So that is homework set number 6 for ECE 341.